Thank you all for being here and welcome to PSC. We're very happy to be hosting this event here in these brand new facilities. And I'd like to thank our different partners, AMS, Agence numérique en santé, Inserm, Inria, and of course PSC, PariSanté Campus. I don't know how we say it in English, but the management team and Mr. Antoine Neuraz here. My name is Benjamin GRELIÉ. I'm the co-founder of Posos, and I'll be introducing our first meetup in NLP healthcare. So there's two goals about creating this NLP meetup. First is about growing a community that we think doesn't quite exist, and build expertise, partnerships around a common goal. And second is to be able to share experiences and best practice and make that community foster new ideas. We think that NLP is one of the major enablers towards a better healthcare systems, and we're very happy to be here to present you with different advancements and opportunities that our hosts will be talking about. We've found out that during our history with Posos that there's lots of natural unstructured data in the healthcare system, and there's enormous work to be done to make that data more available. We've discovered also that mostly 80% of the PDFs contain knowledgeable data. As you all know, PDFs are not a very computerized, exploitable data format, so that's a pretty big and tough challenge. And yeah, that's about it, I guess. Again, we're very happy to have you all here. And just a quick note about Posos. Posos is a French care medical company, and we built a clinical decision support system. It's used by about 35,000 doctors and physicians, and more or less 60,000 healthcare professionals. And we're currently deploying in the healthcare facilities throughout France, and we're hosting this first event. I'll be passing along to Xavier, which will introduce our different speakers. And I wish you have a pleasant evening, and hope to meet you soon. Thank you.
Thank you, Benjamin. I'm really happy to welcome you all to this first occurrence of the Healthcare NLP Meetup, and more especially our four speakers, François, Patricio, Antoine, and Perceval, who have kindly accepted our invitation to share their work this evening. So each presentation, we will have 3 presentations, and each of them will last approximately 20 minutes, and will be followed by a sequence of questions. So feel free to ask your question either in the chat, if you are online, or at the end of the presentation. And now we'll begin with François Plesse and Patricio Cerda. So François is data scientist at Posos, and he holds a PhD in computer vision from the Centre d'études atomiques. And Patricio is also a data scientist at Posos, holds a PhD in machine learning. And they will talk about the challenges that we faced here at Posos to build a prescription support tool, and all the ideas and techniques have implemented to overcome these challenges.
Thank you. Good evening, everyone. So first, I would like to present to you some of the challenges that we faced when building NLP models for our prescription support tools, some of the constraints that we set, and what we learned during this work, and hope that some of it might be useful to you in your own work. So first, the problem that we are aiming to tackle is to provide some answers to physicians who are asking questions such as what kind of drug they can give to a woman during her pregnancy, or for example, can 2 drugs be given to a patient with a specific diseases. And this information does not exist directly in this exact form, which is why we have to analyze these questions and specify the correct information to match them with the structured data that is available. One specificity of this problem is that since we are tackling patient prescriptions, we cannot allow any errors, because that could have very serious consequences for the patients. And also one added benefit is that if we manage to do this, it can also allow us to share data with other systems that use the same ontologies. And thus the first problem that we are aiming to tackle is the named entity recognition problem, which aims to match query with the corresponding data. And for this, we first want to recognize the entities and the medical entities in this case in the sentence, such as diseases and drugs, drug dosages. And for this, we manually annotated a data set of around 400,000 sentences, which come from diverse scientific sources. We trained a token classifier model with two base models, with BiLSTM and CRF, and the BERT-based model. We also annotated some user queries, because since the final use case that we are aiming to tackle is to match these queries with structured data, we also want to make sure that this model works well on these queries. And we have around 3,000 queries, which we think is not enough to train a model, but can be enough for test purposes. And thus we will report two metrics on these two data sets. And finally, since our philosophy is that no model can have a 100% success rate, which is why we always want to show the physicians the intermediary result of the model and have some fallbacks in case the model fails. Our first result on this task showed us that this method was not enough to answer our problem, and mainly one of our hypotheses was that the discrepancies between the train and inference data was preventing the model from correctly detecting the medical entities, and mostly the diagnosis, which proved to be the most difficult entity to recognize. And because in our train data set, we had complete sentences with around 25 words per sentence, whereas in the inference, the users were mostly entering keyword queries with 2 to 3 words. And one of the major problems of this was that they removed all the context from the sentence, and this made mostly the segmentation of the entities harder. Which is why we aimed to put the training setting closer to the inference setting, and one of the constraints was that we didn't want to make any new training data set with the new annotation phase, because that was very costly and time consuming. Thus, we used a new approach, which was to use synthetic data to simulate the user queries. The two main approaches. So first we downsampled some samples, because the users all had entities in their queries, whereas in the scientific sources there were many sentences without any entity. And mostly we simulated some examples in two ways. The first was taking the sentence from the scientific source and removing all the context, all the non-entity words, which made some realistic examples that the users could maybe enter in the platform, and this would keep the internal consistency of the entities in the sentence. And the second approach was to use templates. We have a small data set of around 1,000 templates with entity types and the rest of the sentence, and this is filled by random entities of the same type. And this has two purposes. First, is it trains the model to be invariant to the entity of the same type, which was inspired by a work of from ACL 2020. And the second was that it also simulated some short user queries that the users could enter. Some results. The first one was the result on our first dataset on the sentences, which showed that the synthetic data did not improve much on this dataset, but it wasn't supposed to, because our goal was to be able to better match the queries without any keyword, and the accuracy on the query test set, which is comprised of user queries, showed us that the template data really helped us improve the segmentation part, because as you can see, so there are three lines here. The first one is the accuracy of the name entity recognition, which performs quite well anywhere around 96 to 97% accuracy. But the main problem we still had was the name entity linking, which takes the outputs of the recognition part and tries to link it to an ontology. And this was really helped by the better segmentation of the model, with around 6% improvement. Some takeaways from this first model was that we really think that exploring the training data helped us spot some problems in the annotations, and also the shift between the data in France and training. This showed us one way of improving the data, which was to use data augmentation. And finally, some perspectives. We are aiming to use this model for perception structuration, and we also want to still improve the segmentation, because the name entity, we think this is still taking this is the main bottleneck for the name entity linking part. So now we'll present a second model, the intent classification with Patricio.
Hello, thank you all for being here today. So I'm going to present right now a second model that we developed at Posos. No, I think it's fine. It's fine. It's fine. Okay, so it's an intent classification model that, if you don't know Posos, it's like the homepage. It looks kind of like that. So the idea of that is that people can go directly to find the medical doctors can go directly to find the information they need, like side effects or interactions or alternative to drugs. And but it's kind of difficult if you don't know the website. So we develop an intent classification model so people can type directly the question, and we recommend which of these modules is the most appropriate given the question. So what are the challenges of this intent classification model? So first of all, it needs to adapt to our changing environment, because imagine that we have some new module and we need to detect new intentions, and the model needs to be trained, so this needs to be, we need to respond rapidly to that. Also, it needs to be robust to typos, so of course if you don't know exactly the name of the medicine or the drug, it needs to be robust to that. And sometimes if we don't understand your question, we will fall back to our search engine, where thousands of documents, and you maybe will find the answer there. So this is a little example. So if you type this question, for example, we recommend that the most probably the model that corresponds the best to the question is the interactions and contraindications. And with the name entity recognition model, we will be able to detect the drug and baby, the word baby, that might be useful in the question. And of course, also we have another module that may respond to the question, which is the drugs module. The contraindications part will respond to that question. So then I'll do a quick demo so you can understand a little bit better that. So what is the data set for that? So we use the same templates.
Le micro. Le micro. Ouais, ouais, il faut le prendre.
Okay. We use the same templates that François used in the numeric recognition model. We use it to train this intent classification model, and the idea is to the dataset is much less complex with this type of questions because it's generic. So, for example, we have more than 30 intents, and the idea is that with maybe 100 examples for each intent, we are able to train an intent classification model, which is big. It would be much more if we have like specific questions. So the input is data set, and then a simple model to train would be to take this templates data set. We use words embeddings plus character engrams to account for both syntax and semantics of the question, and then we can use any tree-based model like gradient boosting to give the inference part. So we train the model, and the performance is around 80%, which is not that bad because we have 35 intents, I think. So it's kind of a difficult problem. Okay, so then the inference part would be like you take a query from a doctor, and the name recognition model and linking will transform this question in a template, and then the inference is going to be correct. We have like the output here could be that the most probably input is therapeutic alternative. Okay, so now I have a quick demo of this. You can see. So I'm allergic to pollen, so I did an example with that. So for example, cetirizine parfois remplace. Donc là, ça c'est that's the homepage of the website, and then they propose you the alternatives, so the equivalents to this drug, and if you click there, and then for me it's rhinite allergique, and then you have all we propose all the equivalents of this drug for the same therapeutic class and for other classes. For example, I use, and then you can also filter here by adulte dans les formes saisonnières. Okay, so then you have for example, I'm now using I use the cetirizine. Okay, so how does this look in our API? So it's the same question, cetirizine parfois en tête. Et ici, je peux mettre des typos, I can put typos. It should work. So the probability of the drugs alternatives module, it would be 66%, given the typos. Here you see like we take the query and we mask it, and we have all the information, all the entities detected in the question. Yeah. So the advantage of this model is that it's really easy to train, and we use the name entity recognition part to train it, so it's kind of direct. Okay, so now other models that we're working on are the base name entity recognition linking. We didn't talk about the linking part in this presentation, but it's also a very complex problem. We also have a dosage entity detection because we have a scan. We can scan the prescription and then detect all the drugs in the prescription. We can detect the dosages, so we have to develop that, and also we have if you have some research projects related to this, so we can maybe propose to share these APIs with you. Maybe it would be interest for some benchmark, for example. And then the knowledge extraction part, it's so you have text, and we want to identify some important information in text, like paragraphs, and we're also developing models on that. Okay, so some conclusions about this part. first of all, for any model, NLP model that's in production, you need to try to be able to solve errors quickly. So you need to think about synonyms, for example, exact matches or fallbacks, pipelines that will be able to solve your problem very fast. Also, you need to try to use input metrics to verify the coherence between the data used to train the model and the data that's really going into production. So users asking questions. And finally, so it's like François in his presentation showed, that it's often preferable to improve the quality of the data rather than the model, because the model may change a little bit, but it's not the more important part. Thank you. I know you have some questions. If not,
Does anyone has a question in the room? So I think we have already one question in the chat, but if you have other questions, you can ask them in the chat. So the first question is, are the APIs open accessible?
you can ask. So yeah, maybe if you have some research projects that are similar, that work about similar models, yeah, maybe we can share with you the APIs so you can work as a benchmark, or maybe even discuss about the different algorithms to solve the problem. So yeah, that's the only one.
Yes.
Thank you for this presentation. Did you use any other kind of information, because French annotated data is quite scarce, and often it's a challenge to try and find other sources of data. And so I noticed that you normalize to medicaments, to drugs. Did you only annotate data to do this part, or did you?
Are you talking about like the data set with templates, or?
Yeah, for example, yes.
So this is the only input to the model plus the name entity recognition part.
Okay.
And then we have other types of entities like drug, diagnosis, we have dosages, and therapeutic classes. So these are generic, less complex questions. And then, yeah, I think some intents have maybe 200 or 300 questions per intention. Another one maybe with 50 it's enough, because they are not complex, not so much complex. And it works pretty well. We tried to have a much bigger. Before we had a much bigger data set with I don't know, 20,000 questions, but instead of drug, just a specific drug, for example, or a specific diagnosis, and the model is kind of difficult for the model to generalize from that. Thanks.
Yeah, thank you for this presentation. It was very interesting. I have two questions. One for the first presentation. I wonder, when you use synthetic data, you transform the natural language questions to keywords. Did you remove all the full sentences from the training set, or did you mix?
No, we kept the original sentences and only added a smaller sample of synthetic data. We tried with different parts of each, and it performed better when we kept mostly still the full sentences and some of the synthetic data.
Nice. Somebody else.
So there are other questions on the chat. So the first one is it's a question from Imen Bakour, who asked can you precise the method or loss function you use for validation?
For validation, for the analytical recognition, the loss function was basically the multiple classifier. Cross entropy loss, and during the validation, the metric that was compared was the F1 score, only on the first data sets, and then it was only for testing purposes that we used the accuracy on the user test set. The whole training part was done with the cross entropy loss.
Okay, another question. When you use the Bertner model, is there any method to annotate tokens automatically, and how did you annotate them?
We annotated them manually with pharmaceutical students, and we have not tried any method for automatic annotation. The thing we are trying right now is to use some rule-based annotations, some rule-based methods to get a first annotation of the data set. That's for the model we are working on the prescription analysis tool. But this is still a work in progress. I don't have any result for now.
Maybe the IOB system for annotation.
Okay, so is there a last question here in the room? Although I think we can thank again François and Patricio for the presentation. And François and Patricio have told us about how to use name entity recognition and linking and intent classification to build a prescription tool. But these modules can be used for other applications. And for example, we want to use them at Posos to perform data extraction on clinical records. And this is precisely the subject of the second presentation.
How is this?
And so we are pleased to welcome Antoine Neuraz, who is a medical doctor and who also holds a PhD in biomedical informatics, and who is also a researcher at Inria. And he will explain us how natural language processing can be used to extract data and to gather more data in the context of emerging disease. So welcome, thank you for being here.
Thank you for the invitation. So, yeah, today we're talking about natural language processing in the context of a new pandemic and emerging diseases. So we have heard this figure before, but we know that approximately 80% of the pertinent medical data is only present in clinical text, and we cannot have it in any other sources like structured data where we would like to have it to be able to reuse it for secondary purposes. Since a few years now, the medical knowledge is based on evidence-based medicine. And evidence-based medicine is mostly based on structured data because it's way easier to store, to query, and analyze. But unfortunately, when we are talking about structured data, we are talking about forms which are tedious to complete, and the more forms you have, the less data you get. Plus, you have a limited expressivity because you can only use structured vocabularies that are already defined, and you will input only certain data. you will not have things like hypothesis and all the medical intelligence and the reflection of the medical doctors are not present in formulas, but they are present in clinical text. So there is a tension between natural language and structured data. In natural language, we have more expressivity, we have more communication, and more fluidity. On the other side, structured data is better for secondary use, such as in statistical analysis. So our goal here is to take natural language data and to transform it into nice tables so that we can reuse it to answer medical questions. So today I will talk about COVID because now we don't hear about it anymore, so I wanted to remind you of this nice thing. So COVID is an emerging disease, and by definition, at the beginning of the pandemic, we didn't have any specific structured data because we didn't know this disease. And it was a global crisis, so we needed to have rapid responses for research, but also for managing hospitals and managing patients, because we didn't know, for example, which drugs could be harmful for patients having COVID. So here we try to use natural language processing on clinical documents to gather targeted data identified by experts, but also all coming data with no a priori, because we knew that we didn't know anything about this disease. So we needed to be able to do some data mining and discover some new knowledge. So in this presentation, I will show you an application on the analysis of the effect of calcium channel blockers, which are antihypertensive drugs, in patients with COVID. The idea was to know, can we continue to give these drugs to our patients, or are we going to kill them if we don't so? This was the question at the time. We didn't kill them because of that. It's a spoiler. So we used a database, which is a DS-COVID. It's from a data warehouse of APHP. APHP regroups 39 hospitals from the Greater Paris hospitals. And in May 2020, we had about 80,000 patients in the database. And we used for this study 3 data sources. We used diagnosis codes from ICD-10, which is a coding terminology, and structured drug prescription for the structured data. And on the other side, we used the clinical text. So this is the NLP pipeline that we deployed. Yeah. We have a first part here. We take all the data from the data warehouse, and then we have a common pipeline with symptom detection, hypothesis detection, subject detection to know whether the sentence was about the patient or his family or his dog, sometimes. And also negation to know if the part of the sentence was negated or not. And after that, we had 3 different heads. The first head here for targeted phenotypes, for which we used a basic rule-based approach. So we detected about 60 different phenotypes using this. We had also another approach, which was a dictionary-based approach. So we got all the medical concepts from UMLS. UMLS is a metathesaurus, which we groups, a lot of medical terminology. And the third head here, which was for medication extraction. So specifically, we targeted all the medications and all the attributes that were associated with it. And we integrated all the data together and put it back in the data warehouse in a structured format. So this arrow here maybe is the more important because this allowed all the research community to use this data for their own research and not only us to work with. So, as it is an NLP Meetup, I'll focus on the medication extraction part. So, what am I talking about when I'm talking about medication information? We're talking about some sentences like this one, which is like a prescription. So, if I had only this type of sentences, we wouldn't be here because it would be very easy to extract. Just with some regular expressions and pattern matching, we would be able to find every information we need. Unfortunately, we don't have only this type of sentences. Sorry, I didn't translate it, but it was a bit more difficult. So we have also very narrative sentences, and we will see them mainly in medical history of the patients. And if we use just complete matching, the pattern matching on this type of sentences, we'll have a lot of false positive, we'll have a lot of past information, or also false negative, because there are in the clinical text a lot of misspelling and typos. So we did use a machine learning approach, and as we didn't have any data set available at the time, we annotated the data set of 300 documents, and we trained some model. So we trained the BERT plus DLSTM CRF to extract this kind of information that we have here. So we have the drugs, the dosage, the frequency, conditions, routes of administration, the start of the administration, the frequency, and we also extracted the relations between the drug mentions and their attributes, because in the same sentence we could have more than one drug, so we needed to know which for which was it, and so we used for this some meta entities instead of using a standard relation. So we extracted the relation in the form of large entities that were aggregating all the drug mentions and their information. So the model was a sequential model. We used the BERT embedding, followed by a VLSTM CRF, which were used to extract the entities. And afterwards, we combined the output of the first model with the original BERT embeddings to extract the drug blobs, so the relation between the entities. And we compared this to a Paleolithic model. I mean, it was before that, so it's very story. It was Elmo with a BLSTM with some rules. Okay, so with no surprise, BERT was better than every other model, but interestingly, we take BERT was the best model, sorry. And we see also for the extraction of relations that we gain almost 40 points of F-score with the second model. There was some disparities depending on depending on the entity types, mainly because of the support, because some of the classes were more rare than others. And if we compare to state-of-the-art models, we can see that we are in par in terms of performance. So back to the COVID case now. If we look at the volume of data that we were able to extract from text or from structured data, we can see that in terms of medications, we have almost 7 times more information in the text than in the structured data, and 15 times the number of phenotypes in the text. Here we focus on a series of concepts and phenotypes that are specific to COVID, and we can see in blue that the main part of information is present only in the text. The numbers here are the number of patients that for which we were able to find the information. And for example, for 2 concepts that we know now are really associated with COVID, anosmia and agasia, it was only present in the text and not in the structured data. We can see also that when we extract information from the text, we can have a longer history, but this part is mainly due to the dynamic of deployment of the EHR in the hospitals, which was deployed gradually. So if we do the same now, we won't have the same difference. So we compared from our 80,000 patients, we selected patients with COVID-19, and we compared extracting data from structured data or NLP, and we can see that if we use NLP, we have 3 times more patients for our study. So here we perform the multivariate survival analysis. So in the plain English, we observe if there are higher risk of death in the different groups, and here we compare the effect of the different variables. The vertical dotted line is 1, so if we cross this line, there is no effect on the survival. On the right, there is a detrimental effect, so a higher risk of death, and on the left, a lower risk of death given this variable. So you can see, for example, that the older we are, the more we have. Yeah, it's research. And in blue, if we look at the results with the clinical text, we can see that the first thing to see is that we have very the results that we see here are coherent between the text and the structure and the clinical text, the structured data. So we are not telling what we are seeing is correct. And we can also see that when we had the patient from the clinical text, we can see here that we don't cross the line anymore. And it means that we have achieved a statistically significant result. So we can see here that the patients with calcium channel blockers are less likely to die than the other ones. So this answers our initial question. So in conclusion, NLP is useful in the context of emerging disease because we can get some relevant information, and we were able to deploy it in 2 weeks on our house, but it was also allowed because we had some pre-existing work on and specifically for medication information, because the annotation of the dataset took about 2 months, something like this. So it was done before the crisis. And as I said earlier, we were able to put the data back in the data warehouse so that other research teams could use it, and more than 30 research projects use this data. And it was published in a journal of medical informatics research. So here is the list of the research that were published using this data. And yeah, that's all. Thank you. Of course, it's a teamwork. I was not alone. So if you have any questions.
Vous pourrez pas, ça va être trop court. Il faudra répéter la question au micro. Vous pouvez répéter la question au micro.
Wondering, not a question about NLP or machine learning, unfortunately, but more about the format that you use to structure the data. So maybe tell a bit more about.
Yep. So the question is about the formatting of the data after they were extracted. So we use the OMUP data model, common data model, because our data warehouse is in this format, so we used it. Yeah.
So that it enables to store like links, relationship.
Sorry?
Does it enable to link basically your content, like adding a logic tree or something, things like that?
You mean did we normalize the information?
Yeah, basically like a prescription, something like that. You have links like you special purposes between the entities that you are detecting. So can you anchor these as well in your basically your structural data as a methodology, for instance?
Yeah. So to link the data, we used ATC, which is a terminology for medication, and we decided at this time to use a very basic normalization approach, which was exact matching. So it was more lazier, it's not possible. But the idea was to have 0 false positive, and we accepted to have less linking, less normalization, but we didn't want to have fake information. But we are exploring now more robust methods, or more sensitive using, for example, the coder model, which is a BERT model, which has been fine-tuned on the UMLS, and the terms of the UMLS and the relations between the terms.
So thank you for your presentation. And the question is about labeling. How many cases did you label, and what did you use?
So we used a random sample of clinical text from the data warehouse. So the data warehouse contains right now something like 30 million of documents, and we took a random sample from it, and we annotated manually using BRAT and with the PIO format that answer your question.
But for the study, for this one, how many did you?
For the study, we had in total we processed something like 3 million documents, from the COVID database of APHP. But in this study in particular, we had 80,000 patients. So we made the inference on all the documents from this patient. So to represent, I don't remember exactly how many documents it was. It was a lot.
So thank you. I'm not as technical as you guys, but what I'm interested in is on the structured data. Have you been using a lot the structured data to enrich the unstructured data? So have you been able to match both structured and unstructured? I could see one slide where you put you have the level of importance of the input data versus structured data, and when you add both, so you can see that it's not big when it's both. But the question is also, structured data can be really many of them. You can have many structured data. So which one did you use? Is it only PMSE? Is it the biologic analysis, image, or what kind of? Because I think you can make a hell of a difference in terms of added value, on the analysis. Thank you.
Yeah, it's completely true. In this particular work, we wanted to compare both. Compare structured data to NLP, so we didn't use them both at the same time.
Okay.
But in another paper where we were doing some data mining to try to identify drugs that could have a beneficial or detrimental effect on patients with COVID, we integrated a lot more information. So we used PMSE with ICD codes, we used lab values, we used movements also of the patient in the hospital to know if they were in ICU or if they were in standard ward, and drugs, structured data from drugs.
So you had a better precision afterwards?
It was not it's not very comparable because it's not the same approach, but it's certain that if we use both information, we will have more patients and therefore more statistical power, so we'll have more precise estimations of the different effects.
So we'll take a last question from the chat, which is, I cannot take all the questions, but how did you detect negation?
Negations, we used pattern matching. So it was some regex that we used. It was a sequential approach. We first extracted sentences, and then inside sentences we extracted syntax, which are part of sentences, and after that we classified each syntax to know if it was negated or not. And using this approach, we could have negation information for every downside model that we were using, and we were not dependent on the entity extraction model. But it was a regex approach.
During my PhD thesis, which I defended last year in December, and so the focus of this talk is structured entity extraction in breast imaging reports. So as you may know, and as has been presented by other presenters tonight, a large quantity of information is in textual format and medical. Sorry. And so a medical research, so a large quantity of information is in textual format, and most medical research, patient care, hospital management need some structured data. And so we could use that to follow, to improve the follow-up of patients, build better cohorts, manage services, perform statistical studies. And so for that, we have different tasks. When we try to do NLP on clinical data, we have different tasks of various complexity. So we have, for example, simple entity recognition, also known as named entity recognition. Once we have these entities, we can normalize them, which means map them to a database of concepts, for example, like medicaments, drugs, I mean. And structured entity recognition, which means grouping these different simple bricks extracted from the text remains a challenge. And so this is the main focus of this talk. So speaking about the medical context, we focus on breast cancer detection and breast cancer information extraction from medical reports. And for that, we are going to extract information, for example, to validate or train existing data and train image models. So we need to extract this information to make it queryable and, for example, build training databases for image recognition models. We can also use the extracted information to detect lesion evolutions between different reports, map the reports together, for example, between image reports and anatomopathology reports, and also to improve the selection of cohorts, for example, by enabling better queries or more specific queries on the kind of lesion that we have found in a patient. So when I speak about these different entities that we want to extract from the reports, they quickly become quite complex. For example, in this study, we studied different kind of entities, the cancer risks, the breast density, the diagnostic procedures, the therapeutic procedure, the radiological lesion, and all of these structured entities have different fields that we need to extract from the text. And so you can see, for example, the kind of data that we want to extract here, which is frames or tables with different rows, and in each row we may have a value, an optional justification, and the justification is actually really important because it allows us to explicit why did the machine learning model predict the information it predicted, and also better teach the model. So I spoke about complex entities, and we also have complex documents. So you can see that those documents, those reports describing the medical images are usually long documents. They contain usually typos. We can have ambiguous sections, overlapping and elliptic structures, for example, lists. Since we use PDF to text transformations, we can have artifacts that we need to deal with. And the information, there might be some implicit information, for example, time. If you want to know if a specific object was mentioned at a given time, or is it mentioned in the future or in the past, sometimes there is no specific justification for that in the text. So this implicit information is something that we're going to deal with too. So let's focus on a simple example and extract together lesion entities. So reading through this small excerpt, we can see that we find a first lesion. So we use that to fill a frame. So we fill the values and the justification when we find some. So for example, the temporality, the overlap temporality, which means that the lesion was found at the time of the image is not justified explicitly in the text, but it's implicit. And this lesion is actually referred to as well in the conclusion. So we have a first object, and if we continue reading, we can find that there is a second lesion that is also mentioned at the end of the document. And so you may have noticed that these two lesions overlap in multiple places as they share some common attributes. And this will be something that we are going to need to deal with when designing the model to automate these extractions. And so we also annotated other kind of entities, as I mentioned, for example here, the ultrasound procedure. So we annotated a data set of around of exactly 120 documents that we split between a training set of 80 documents and a test set of 40 documents. And you can see on the right side the graph annotation software, which is the same as Antoine mentioned earlier. And now the model. We want to automate these extractions, so we split the problem in multiple subtasks in a same end-to-end model. So we start by extracting named entities that we are going to use to build our justifications and to know when there is a field. Then we are going to classify these entities or normalize them to find the values these fields contain. And once we have all these ungrouped fields in the document, we are going to group them into frames. And so this is the frame extraction part. And finally, since these frames may have missing implicit information, we're going to fill in this missing information using frame classification. So as often in NLP tasks, we want first to obtain contextualized word embeddings, and for that we use sentence-wise BERT followed by a set of bi-directional LSTM layers on the whole document. And so these embeddings are going to be useful for every other kind of every decoders that I'm going to describe next. So the named entity recognition, it has been mentioned before tonight. And so we extract potential fields, we highlight some phrases in the document automatically. And so for that we use a nested named entity recognition model with stacked conditional random field models and Buell scheme. And so at the end of this step we have named entities which are going to be the building bricks of our extractions. And with those extracted named entities, we classify each one of them to obtain the values that are going to be the content of our frames. So for example, 6 months ago, we want to extract the fact that it's classified as a past entity, bilateral, it's both left and right, etc. Now, the main focus of this presentation, which is the frame extraction. How do we group these different entities together? And for that, we're going to build a graph. And to build this graph, from the annotated the results of the first two steps I mentioned before, we're going to ask a question for every pair of mentions, extracted mentions, which is, do these two mentions entities belong to the same frame? And so we're going to ask this for every pair of mention and let the model learn and predict this. And once the model has predicted every hopefully correct relation between the entities, we can perform click extractions, which means extracting the largest group where all entities agree with each other on being part of the same frame. So for example, here you can see that we have a lot of frames, but we can find the two frames that I mentioned earlier when discussing the two lesions that overlapped. And so those two frames overlap in multiple places. For example, left breast cysts are some common fields of these frames and have some distinct mentions as well. For example, 8 o'clock and 6 o'clock. So how do we decide if two entities should be linked together? We could simply match the embeddings together by performing some dot product or something like this. And we will do that, but not only. We can try to improve this with another model. And for that, we are going to use the concept of, to introduce the concept of scope relations. So a scope, as described on the left and the right side of the screen, is a text area on which an entity conveys its meaning. So for example, left conveys its meaning on the full paragraph below it. And so we're going to mix this kind of relation with the simple matching that I mentioned earlier. And scopes are asymmetric relations. So for example, left contains some 2 centimeter is in the scope of left, but left might not be in the scope of 2 centimeter. And most importantly, these scopes are latent, so the model will need to learn them on its own since we did not annotate any scope. We only know which mentions should be together, and this was the data we annotated. So for example, as I mentioned, left has a scope that's below it and is inside the scope of ultrasound and breast. And 3 centimeter contains 8 o'clock, or is likely to contain 8 o'clock, and to be itself in the scope of other entities. So without deep diving inside this model, you can see that this is the frame extraction model, and on the left side you can see the scope relations, scores that we extracted. On the right side, the simple relations. And we mix those 2 kinds of relations together to extract a graph and perform click extraction of this graph to finally obtain the prediction, which is hopefully the distinct entity. And the last part is to fill in the mandatory fields, for example, the temporality, that were not explicitly found in the text using a constraint classification model. So to help a bit the model to train on this data, because the data is actually quite scarce. We have only 80 documents to train the model on. We automatically build some synthetic dummy sentences from a small lexicon. And so you can see these dummy sentences on the right side. We mix them with our original corpus. And the other trick to help the model learn is to filter out illegal relation when building the graph. So for example, we know that mammography cannot be performed on an organ other than the breast. And so we can tell that information piece to the model so that it does not have to learn it. And so without diving inside the results, also we perform different kind of evaluations with approximate field, name entity evaluation, frame support, which measures how well we found the justifications of our frames, the frame label, which measures how well we found the values of the frames, and finally some query retrieval metrics, which simulate what we could have, what we could obtain if we wanted to query the reports with our extractions. So we obtain a correct performance given the small number of documents and their complexity. And we can see that as the query grow in complexity, the model has more trouble, of course, retrieving them. For example, to correctly extract the last row of this table, the model needs to correctly find the lesion, its quadrant, its radial clock position, and its size, which means that it's a lot of potential errors. And so, by updating some parts of the architecture and method, we found that adding scope relations drastically improved the frame extraction performance, that adding constraints at training time improved the frame performance too, and that we indeed should augment the data set when there is a few to no data. And so we can see this here. We simulated varied the number of training documents in the data sets. And we found that knowledge injection, especially augmentations, help when there is few to no document. So for example, even with no document, no annotated document at all in the training data sets, we retrieve most of the named entities using the synthetic sentences that I mentioned earlier, which is especially useful when we want to bootstrap a new annotation process. And we also see that the performance improves slowly when we add some more documents, and so this likely means that a lot of more documents are required to improve the performance of the method. And finally, the visualization. So I mentioned the scopes, and we can see what scopes did the model predicted on the example I mentioned earlier. And we can see that for each entity, the model predicts a part of the text as its scope. And we can use that to either interpret or debug the results. And you can see, for example, here, the two blobs and the split right here is the split between the two lesions that I mentioned and that overlapped. So what's next? First, as complete and powerful was the breadth annotation software, it lacked some customization features and made the annotation process quite tedious. And so this led us to develop a new annotation software that should in theory be better fit for structured entity extraction and annotated these complex entities. And the most important part is to put this model into production and share it. And so the APHP data science team has developed a library, an open source library for this NLP, and built on Spacey. And the idea would be to integrate this architecture in this library to enable reuse by the community and to be able to deploy it on the clinical data warehouse. Thank you a lot for your attention. So don't hesitate if you have any question, and otherwise you can, of course, contact me later or chat with me later.
We'll begin by a chat question, which is why would you only extract the largest group and ignoring other entities?
Why would you or would we extract the largest group? Sorry. Because we extract the largest group because it's every entity that has deemed correct that it is linked with other entities. For example, here, if using this monstrous graph, we extracted only subsets of this graph and not the largest groups, we would likely miss some information. And the large, it's kind of a tricky question. It's because it worked. There is no really. We extracted the largest group because we teach the model to do that because it was relevant for the tasks that we were trying to solve. But to complete a bit, we could have thought of other kind of extraction. For example, extracting not clicks but trees, and these are all research possibilities that I did not explore, but that are really promising as well.
Yes, thank you for sharing your work. I had a question. Did you focus on just breast cancer, or did you have an approach to generalize to other organs in cancer? Because I wonder if so you can apply your latent scopes to other organs and see if the performance can be similar. Or...
So the question was, did we just study breast cancer extraction of entities in breast cancer reports, breast imaging reports, or did we plan to apply it on other kinds of organs? And of course, I would like to apply it on other organs. I've started to discuss with oncology researchers and clinicians to, for example, focus on hepatic lesions. But at this point, it's mostly a problem of gathering the necessary amount of data. And the scheme that I detailed earlier could, of course, be modified to adapt. For example, the organ is, we annotated, for example, other organs when it was not breast organs because it did not interest us. But we could specify this list to include other kind of organs. Thank you.
Any other questions? Okay, so there is the follow-up of the first question. Wouldn't you miss some of the relations in this case?
Would I miss some relations when I'm, the question was, would I miss some relations when I'm only extracting the largest groups of the largest clicks? And I would not miss some relations. I really have trouble finding an example of where it would be useful to not extract the largest groups. The only example where we could have such a case is, for example, if we had deeply nested structural entities. For example, in this case, if we extract the larger group, we indeed find every kind of structured entity that is mentioned in this document. And we don't miss anything if the model predicts it correctly. So sorry, I think I don't know if I answered the question really well, but of course I'm open to discuss it with whoever asked the question later.
Thank you again, Perceval.
Thank you.
And I think Benjamin has a few words to say to you to conclude this meetup.
Yeah, thank you all for your participation. Sorry, it was a real pleasure to have all you speakers. Thank you for the different interventions. It was very interesting, and I can see that there's many use cases. Probably some that we haven't covered, hopefully, and this is an opening for the second event that will be attaining on around the 26th of September, so after the summer vacations. We're open to subjects and proposals, so really feel free to submit topics, and we'll be happy to host it here again in PSC. And that's it for now. There's a small cocktail for the people that are on site, and for all the online people. Well, next time, if you're able, come over to PSC and enjoy a couple of drinks, and we'll be happy to have you here. Thank you all. I wish you a good vacation if you're taking any, and see you in September. Thank you.